Hello guys.
Hi, Professor.
Hi. Hello.
Hello, can you hear us?
Yeah, I can hear. Can you hear me well? Okay.
Yep, can hear you.
All right. All right. So lecture number 4. Today we'll discuss a so-called supplementary cementitious materials. Okay. So these materials can replace a certain percentage of Portland cement. Okay. So typically we also call that pozzolanic materials. Okay. So we showed you what is pozzolanic reaction in early lectures. Okay. And today we're going to discuss these materials. All right. So we have a long history using SCMs or supplementary cementitious materials. This is an example of the famous Pantheon, which is more than 2,000 years ago by ancient Roman. Okay. So in the U.S., the earliest application of SCM is around 1930s when people use slag and flash in the Golden Gate Bridge in San Francisco Bay Area. Okay. So SCM is also called mineral admixtures. So they replace part of the cement depending on the type from 5% for silica film to more than maybe 40% for slag. Okay. So they normally called binder or supplementary cementing or cementitious or cement-based materials. The same thing. So this is a material that when used together with Portland cement, they contribute to the property of hardened concrete through hydraulic or pozzolanic properties, sometimes both hydraulic and pozzolanic activities. The major type of SCMs including flash, which is a byproduct of coal burning process. For flash, we have class C and class F. Okay. We also have metal coating. This is calcium clay. Okay. Silica film, another byproduct. Slag is byproduct of steel manufacturing process. And calcium shell clay. Okay. And pozzolan is the siliceous. Sometimes also has aluminum in it. Okay. Typically in finely divided form, and together with moisture, it will chemically react with calcium hydroxide and to generate CSH. So this is the classic pozzolanic reaction which we discussed earlier. And depending on the source, we have natural pozzolans. Okay. For example, metal coating, red husk ash, volcanic ash, or calcium clay. Okay. We could also have SCM from industry byproduct. Okay. For example, power plants, they use coal as a fuel. Sometimes they also use, they have metallurgical furnace produce cast irons or silicon metal in the case of silica film or slag. Okay. So every year they will generate millions of tons in countries all around the world. Okay. For example, in the US, flash alone, we have around 50 million tons every year. Okay. In China, we may have much more than that. Okay. Dumping these materials into landfill and steams, is first of all a waste of materials. Second, they can also cause serious environmental pollution. So the recycling cost for these materials will be very high. If we can use these materials to replace Portland cement, okay, we have much good environmental impact, and also we can cut down the cost for concrete. We could dispose these materials as concrete aggregate, such as sand, for road-based construction, but this is kind of low-value use because we do not fully utilize its pozzolanic properties. So we do not replace cement with these materials. Okay. With proper quality control, a large amount of these materials can be used to replace cement or used as blended Portland cement as mineral admixtures. So this is the ideal situation to replace cement using these waste materials. So whenever a pozzolanic, sometimes together with cementitious properties, can be used to partially replace cement, it will represent very good energy and cost saving. Again, pozzolanic reaction is siliceous and aluminum materials. By itself, it has no cementing properties, but react with calcium hydroxide together with water, it will generate CSH. Okay, so this is hydration product of C3S and C2S. So calcium hydroxide will combine with pozzolans together with moisture, it will generate CSH again. So this is pozzolanic reaction. So the benefits of pozzolanic reaction is in two folds. First of all, it transfers calcium hydroxide into stronger CSH, so the strength will be increased. Second of all, because calcium hydroxide is soluble in water, and the CSH is not. And also this reaction will increase the total volume of solid. So the porosity of concrete will be reduced because of pozzolanic reaction. So strength will be increased, durability will also be increased as well. So the reaction of pozzolan with calcium hydroxide needs two things. First, it needs water, H, and also it needs time. The reaction is slow, it needs continuous moisture curing. So this is one difference from classic reaction of Portland cement. It is also temperature sensitive, and the high temperature such as steam curing, it will proceed much quicker. So pozzolanic capacity of SCMs, which is tested by direct reaction with calcium hydroxide and monitor how much calcium hydroxide is consumed. Okay. We can see from this table from our textbook, this is a typical pozzolanic capacity of some pozzolans. Okay. For slag, it consumed 40 microgram per gram of calcium hydroxide, okay, which is much smaller compared to silica fume and metakaolin, as well as flash. Okay. However, slag has not only pozzolanic properties but also hydraulic properties, which means slag by itself can generate CSH, so which make it very beneficial to concrete. Then let's look at these different type of SCMs individually. Okay, the first one is flash. It is by far the most used SCM. This is kind of old data. In the US, every year, right now we have around 500 million tons. Okay, in Hawaii, we do not have much flash generated, but still we have more than 300,000 tons every year. So in our small island of Oahu. Okay. And this is the production process of flash. So during the combustion of coal in power plant, so when the power plant burns coal, some of the impurities will melt at high temperature. Okay, and these materials will quickly transported to low temperature zone, and they will solidify as spherical particles because the temperature change, the cooling down is quickly. Okay, much of these particles will fly out with the flue gas. That's the reason we call that flash. Okay. The cost of the flash is actually depending on the location. Typically, it will be cheaper than Portland cement, but here in Hawaii, the price is actually similar or even more than Portland cement. Okay, usually beneficial to concrete. It is widely used in the U.S. and some other foreign country. The use of flash is very much environmentally beneficial because we reduce the recycling cost, and also we replace Portland cement use flash. The size of flash is mostly similar to Portland cement, around 1 to 20 micrometer in diameter. Okay. And most of the particles are spherical in shape, but some of them are partially hollow. They have hollow space inside. Okay. The individual flash particles will vary chemically from each other, but most of them are glassy, okay, but contains some of the crystals. Glassy here means the chemicals are reactive, so we want more glassy phase in flash because the more glassy, the more reactive the chemical, the flash. Okay. The more crystals, the less reactive the material is. In the US, we have generally two types, Class C and Class F. Class C has high calcium oxide. Generally speaking, more than 10% of calcium oxide, we call that Class C flash. Okay. Class C flash normally from western states such as California, Oregon. Okay. Class F has low calcium ash. Okay. They come in from higher quality coals. They come in from mostly eastern states such as New York and New Jersey. And these two classes of flash behave differently in concrete due to amount of calcium oxide in it. And here shows the specs for flash, okay, which is stated in ASTM CEE688 and AASHTO M295. Right. So that standard is performance-based standard. They will specify what is requirement for 7D strengths or 28D strengths for concrete, for example. Right. And the class F flash has glassy phase, which is reacted more slowly. Okay. Crystalline inclusion are more non-reactive substance, such as quartz. So the more glassy phase, the better. Right. And the high calcium flash are little used in European, and low calcium ash is widespread, usually called pulverized fuel ash. So depending on the type of coal used, depending on the location and countries, they have very much different chemicals in the flash. So that will affect the strength as well as the setting time, for example. Okay. So for class F flash, it has only pozzolanic properties. Mostly they have silica and alumina, not too much calcium, not too much C there. For class C flash, it has both pozzolanic and cementitious properties. Cementitious properties means it can form CSH by itself, does not need calcium hydroxide. And flash from Hawaii is not allowed due to high sulfate content. Okay, the sulfate content in our local flash is too high. As a result, it's not allowed to be used in Portland cement. Okay. However, we have ongoing research project trying to use our local high sulfate flash in concrete. This concrete is a totally new type of concrete. It's called alkali activated concrete or geopolymer concrete. Okay. In that concrete, the high sulfate content does not really affect the performance of concrete. So we can use high sulfate content flash in this new alkali activated concrete. Okay. I'm going to show you a video which is about our research project. So we have working on this project for more than 8 years, or 9 years. So this is one video about so-called lunar concrete. Okay. And this is actually a concrete with no Portland cement at all. We use flash together with some other mineral admixtures such as slag to replace 100% Portland cement. Okay.
So this project is a joint project between Pisces and the County of Hawaii to put a sidewalk in here in Hilo, but not an ordinary sidewalk of concrete, but a sidewalk made of basalt. The same basalt that makes up the Hawaiian Islands. The reason that we're interested in this is that Pisces does technology development work on how we can do construction on Moon and Mars. When we go settle Moon and Mars, we can't take construction material with us from the Earth. We have to live off the land, if you will, by using the resources that are there on Moon and Mars. And what we found is that the basalt material on Moon and Mars are exactly like it is on the Hawaiian Islands. And so what we're doing is developing some technologies by testing it here in Hilo of construction using basalt material instead of concrete that we can apply to Moon and Mars. At the same time, we're looking at how we can do similar civil engineering construction here in Hawaii using native material, indigenous material, rather than having to import many thousand tons of concrete from the mainland into the state. If we're able to do that, it would save significant cost in using basalt material instead of concrete for civil engineering projects. This project is very unique because it blends 5 different groups together. The County of Hawaii, the County Research and Development, the state level, which is Pisces, the federal government, which is NASA, the space agency, academia. One of the pads we're putting in is done by the University of Hawaii at Manoa Civil Engineering Department. And then the 5th group is the private sector. One of the pads we're laying down uses, instead of steel and iron rebar, it uses basalt rebar. And that comes to us from Kodiak Rebar in Houston, Texas. So we're very excited about that. And it blends then into this one sidewalk, 5 different groups that are working strategically together to do something very unique, something very different for the state. One of the goals for Pisces is what we call dual-use technology. Not only technology that we can use on Moon and Mars, but technology we can also translate for use in terrestrial applications for the benefit of the state. And this is one of those applications of showing construction technologies that can be used on Moon and Mars, but also that have application within civil engineering projects within the state of Hawaii, within the Isles. Sidewalks, streets, patios, piers, berms, foundations, all that might be able to be made out of basalt material instead of concrete. So over the next year, we're going to be evaluating different options for assessing the pads here on the sidewalk. Compressibility test, tensile strength. We're going to be taking cores out that University of Hawaii Manoa will evaluate, and then see how these pads perform over the course of a year. So perhaps a year or 2 from now, we could move into other civil engineering projects within Hilo, Big Island, across the Isles out of basalt instead of concrete.
New Year. All right. Okay. So this project is around 5 years ago, 2015. We use no cement, just flash and slag. Okay, and after that we have multiple projects coming from Federal Highway and Hawaii DOT. Continue this research on cement-free concrete. The performance of this so-called alkali activity concrete is very good. And also we can reduce the total cost, and also of course the environmental benefits is huge, okay, because we do not use any Portland cement. Instead we use the waste materials okay, in the concrete. All right. So here is the scanning electron microscope picture for flash. As we can see, most of the particles are spherical in shape. Some of the particle is hollow inside, some empty space in the flash. The average diameter for flash is around 10 to 15 micrometer. Okay, and because the shape of flash is almost perfectly spherical. So when we introduce in concrete, it can make the concrete easier to mix. Okay, increase the slump. Okay. So this is how the flash will affect how much water is needed in concrete. As we can see, we can reduce amount of water requirement compared to control, which is concrete with 100% of cement. This is due to the so-called ball bearing effect. The spherical shape of flash will facilitate the mixing of concrete. Alright, so this is flash. The second one we're going to look at is called silica fume. Silica fume, let's look at introduction, is finely divided residue from production of silicon, ferrosilicon, or silica containing alloy. Okay. And this is the byproduct of induction of arc furnace. Okay. And a reduction of coarse into silicon at very, very high temperature. Okay. And when the temperature cools down quickly, we have these tiny spherical particles consisting mostly non-crystalline silica. Again, non-crystalline means it is very, very reactive. The particle size of silica film is also very small. It's about 100 times smaller, only 1% of the size of Portland cement. So make it very reactive, and also the cost-wise is very expensive, around 10 times the cost of Portland cement. So the reason we use silica film in concrete is not to cut down the cost, is to improve the performance. Actually, for all type of high-strength concrete, we usually use around 5 to 15% of silica film. Silica film can greatly enhance the strength of concrete. So it is essential for high-strength concrete. It has pretty high alkali content and also mostly glassy materials. Particle size, again, is very, very small, 0.001 micrometer. But sometimes the particle can be stick together. That may cause a potential problems if the particle will stick together. The potential problem is called alkali silica reaction, or ASR. This is one of the potential problems for concrete. We'll discuss about that in future lectures. Silica film will react very quickly. Okay. When used properly, it can modify the fresh concrete properties and greatly increase the strength, and also make the concrete very much impermeable. So make the concrete stronger and also more durable if used correctly. So here shows the particles of silica film. Again, very, very small, spherical shape. Cement, angular shape. Flash, spherical shape, similar size to cement. Okay, this is ultra high flash, smaller than typical flash, but still the size is around 1 or 2 to 5 micrometer. So silica film is much smaller. So one of the reasons silica film can increase the strength of concrete net barge is due to the so-called filler effect. Okay. So what is a filler effect? So the so-called filler effect is because the particle size of silicon film is so small. Okay, let's say this are cement. Cement particles is around 10-15 micrometer in size, and silicon film is like 1% the size of cement. So when we introduce silicon film, it will try to pack the interparticle space between cement. So which means we can increase the so-called packing density. So packing density means how much particles, how much solid we can put in a certain volume of empty space. Because the size of silicon film is so small, it can act as a filler. Okay, so increase packing density. So as a result, we have a denser hydration product. Okay, that will in turn reduce the size of the pores. Okay, and also reduce the water requirement if with a certain type of chemical admixtures. It's called superplasticizer. Plasticizer. Okay, we're gonna talk about that in details in future lectures. And also increase the strength of concrete. And also because silicon film is very, very reactive. Okay, 99% is highly reactive silicon. Okay, so that will make the concrete stronger, contribute to the strength of concrete also. Next, the next one is called ground granulated iron blast furnace slag. So slag is coming from steel production process. Okay, the liquid slag is rapidly quenched from high temperature to low temperature. Again, it will become glassy or reactive. Okay, remember, the more glassy phase, the more reactive the material will be. Increase the reactivity. All right. The water quenched product is called granulated slag because the particle size is similar to sand. Due to high calcium oxide percentage, okay, slag has self-cementing properties or cementitious properties, which means it can form CSH by itself, but the reaction is slow. Okay, and because it has self-cementing properties, we can use much higher percentage than other mineral admixtures. Okay. The glass also has calcium, aluminum, sometimes magnesium, and also silicon. The specs for GGBS is for ground granulated blast furnace slag. Is from ASTM CEE688. Okay, because it can form CSH by itself. However, it needs some kind of activation. Okay, we need some type of high pH environment. From hydration of Portland cement. So they have different grade from grade 80 to grade 120. So that is based on so-called activity index. Which is simply defined as the ratio of the strengths at 28 days of the specimen with 50% of slag plus 50% of cement over the strength of the control mix. So F28 means the compressive strength of the specimen as 28 days. Okay, the specimen of the control, which is 100% cement. Other properties such as water cement ratio will be the same. So we get the ratio of the control and the 50% slag and 50% cement. Grid 120 means the activity index will be equal to 1.2, which means 20% higher strength when we use 50% of slag. Okay. The price of slag will be similar to Portland cement. Okay. Again, it's depending on the location, but generally speaking, the cost is similar to cement. The reaction of slag with cement is slow. Okay, take months or even years. Okay, but eventually it may provide stronger concrete, and also the concrete tends to be much less impermeable. So the permeability of the concrete will be lower. People care about how long the concrete can last. We call that concrete durability. So the most important factor control the concrete durability is so-called permeability, or how easy water and air can penetrate the concrete. So slag can reduce the permeability, make the concrete very durable. So when concrete is in contact with seawater, or we care about corrosion of reinforcement, we may consider use slag. The next posing length is called metakaolin. It's coming from kaolin, which is the clay, the type of clay. Right. So the kaolin clay is dehydroxylated, which means we get rid of hydroxide ions by heating up the clay to 6 degrees Celsius. Okay. The particle size is smaller than Portland cement, less than 5 micrometer. The reactivity is also pretty quick. The surface area of metakaolin is also higher compared to cement, also contribute to its higher reactivity. Okay. Metakaolin can also make the concrete less permeable, can also reduce the alkali concentration if alkali silica reaction is a concern. Again, we talk about ASR or alkali silica reaction in future lectures. Alright, we can also get pozzolan from res husk in res husk ash. Okay, so this is made by burning the res husk. But the burning process is well controlled. So otherwise we may not have too much reactive ash. Okay. So the highly pozzolanic ash can be produced by controlled combustion. Oh, sorry, here. Controlled combustion when the silica is retained in non-crystalline form. Okay, again, non-crystalline form means it is more glassy or more reactive. Okay. And for every 200 kilogram of husk, we can get around 40 kilogram of res husk ash. Okay. We can also get pozzolans from natural source, such as volcanic rocks and minerals. Okay, and in Hawaii we have a lot of volcanic ash, but in the policy the law does not allow us to use our local volcanic ash in concrete. Okay, but some other places we can use that. So during the explosive volcanic eruption, if the cooling process is quick, we may have reactive or glassy phases in the volcanic ash. We may have different classification of volcanic materials, such as volcanic glasses. This is some of the example of the source of the volcanic glasses. Okay, and volcanic turf. This is pozzolans from Italy or Germany. Calcite, clay, and shell is also belong to natural pozzolans. Okay, also again depending on the heat treatment. If the temperature is cooling down quickly, it will be more reactive. Okay. We could also have natural pozzolans from organic origins, such as this is the so-called diatomorous earth. This is a group of pozzolans from organic origin. Okay, we can get that from algae, such as states from California. And this table compares the basic property of typical pozzolans with Portland cement. Okay. As we can see, the particle size of cement is similar to natural pozzolans, and the flash for silica film is much smaller. Okay. The surface area flash is similar to Portland cement, so does natural pozzolans, but for silica film it is much higher. Okay. Higher surface area also means the reactivity will be higher because we have more contact area between water and these materials. So higher surface area, we have higher reactivity. And look at red husk ash. It is even higher in surface area compared to silica film. So make it red husk ash very reactive. For particle shape, flash and silica film is spherical shape. For red husk ash, it is cellular, irregular, which means some of the particles is hollow inside. That's one of the reasons it is also has very high surface area. And here shows the specific gravity. This table shows us the chemical composition of typical pozzolans. Okay, please focus on silica, alumina, and also calcium oxide. Okay, so some of these materials has mainly silica and alumina, like class F flash. Okay, and the silica film. Silica film has mostly silica. Okay, so that means these materials has only pozzolanic properties because they have only silica. Okay. For class C flash and slag, they have a certain amount of calcium oxide. Okay. The calcium oxide percentage for class C, this is a typical value. It may change depending on the source. So, but for class C flash, it have more than 10% of calcium oxide. For slag, it is even higher. So that tells us for class C flash and slag, they have both pozzolanic properties and hydraulic properties, which means these materials can form CSH by themselves. Okay, so here shows the XRD, which is X-ray diffraction of different type of materials. Here is the slag. Here is high calcium flash. Okay, so from XRD, if we see a lot of sharp peaks, so that means they have more crystalline fraction. So more crystalline fraction means the material will be less reactive. More glassy fraction, which means it does not have very distinguishable peaks. Instead we have this so-called diffusion band. Okay, for example, a slag, then this material will be more glassy or more reactive. Okay. Typical amount of SEM in concrete. This is kind of old information. For flash, class F, we can use up to 20%, class C up to 40%, slag to 40%. Okay, but nowadays we can use up to 100% of these materials. No cement at all, like we just discussed in the video of lunar concrete. Okay. Mechanism of actions. Let's look at how these materials can affect fresh properties and also hardened properties. Okay. So the materials can control bleeding. What is bleeding? So in concrete, bleeding means the separation of water from cement. If a concrete has bleeding problems, we may see on top of the concrete we have a layer of water. So we call that bleeding. Okay. So introduce these materials can reduce the bleeding. Okay. By green refinement, because pozzolans can transfer the larger calcium hydroxide into smaller CSH. Can also reduce the porosity, so that will also be helpful to control the bleeding. Okay. So when we have bleeding or segregation problems, segregation means the separation of the large stone of, so we call coarse aggregate with mortar or cement paste. Okay. So incorporation of flash can improve the workability by reducing the size and also reduce the volume of the voids. The finer the mineral admixtures, less will be the amount needed for enhancement of cohesiveness and the workability of concrete. Okay. Here again are two new words. So workability is, when we mix the concrete, we need to consolidate the concrete. We need to transfer a certain amount of energy to make the concrete fully compacted. Okay. So workability means how much energy we need to consolidate the concrete. Better workability means we need less amount of consolidation. Cohesiveness means how easy the concrete will segregate or bleed. The small size and glassy texture of flash and slag make it possible to reduce the amount of water required for given consistency. So consistency means how easy the concrete can flow. Okay. So basically flash will improve the workability of concrete. All type of mineral admixtures will improve the cohesiveness and also workability. But sometimes they do not have the water reducing capacity of flash and slag. Okay. Flash and slag can reduce the amount of water required for concrete due to the ball bearing effect, the spherical shape of the flash. Okay. If the materials has high surface area, such as permides or red cast ash, and also silica film, that high surface area can increase how much water is needed for concrete. Okay, so keep that in mind, especially silica film. When you introduce silica film in the system, you will notice we need much higher water to make the concrete workable. We can use water reducing admixtures such as superplasticizer to compensate for that. So this table summarizes the effect of SEM on flash properties, okay, such as water requirement, workability, heat of hydration, and setting time. Okay, you can just have a look of that. For hardened properties, this is a long-term strength development. Here compares the strength of concrete without flash, which is the blue squares. Okay. With flash, this is the red cross. As we can see, without flash, the strength will basically flat, no increase after around 100 days, 3 months. Okay. But with flash, the strength will keep increase over 1,000 days, 3 years or more. Okay. This is because pozzolanic reaction. We need water and also time. Okay, so give concrete with flash a little more time for the strength to increase. This figure shows how the temperature affects the strength development up to 90 days, 3 months. Okay, so the control mix, which is the blue line, is 100% flash. Okay, and the other lines, which is flash, the green line is flash with 20% of S. So basically it means 20% replace of cement. The purple lines is flash with 10% of cement and 10% of sand. Okay, the red line is another 20%, 20% actual flash by mass of cement. But generally, this is introduced around 20% of cement flash into the system. So compared with the control, which is 100% cement, we can see at early age, up to a month, the control mix has higher strength. Again, this is because pozzolanic reaction is slow. It needs time to catch up. So after the first month, the strength will be higher compared to the control mix. Okay. For silica film, this is pretty different. Okay, the red line is 10 silica film, which means 10% of the cement is replaced by silica film. The control mix is again 100% of cement. Because silica film is very, very reactive, and also the particle size of silica film is small, the surface area of silica film is very, very high. So that means silica film is very reactive. So that will compensate the slow reaction of pozzolanic reaction. As a result, concrete with silica film, the strength will not be lower at early age. So at early age, the strength will not be lower, and at later age, the strength will be higher compared to the control. So at the beginning, the concrete with silica film will not have lower strength. At later age, the strength will be even higher. then let's look at how these materials will affect durability. Okay, so mineral admixtures typically they will reduce the temperature rise because again pozzolanic reaction is slow, so the temperature rise at early age will be not as high as 100% cement. However, silica film may be an exception because silica film is very reactive. The temperature with silica film, the concrete may have even higher temperature. Okay, so admixtures may not react to significant degree for several days, and the heat of hydration will be much lower, about 50% less compared to the control mix. The permeability of concrete play a fundamental role in the rate of deterioration. In other words, permeability of concrete is the most important factor control concrete durability. The lower, the better. The lower permeability, the better durability of concrete. Okay, such as control of acidic reaction or attack by acid or sulfate solution in the case of sulfate attack. That is because pozzolanic reaction will reduce the pore size. We call that pore refinement. Refinement can also reduce the porosity or the percentage of pore volume in concrete. So that will improve the chemical durability containing mineral admixtures. So mineral admixtures can improve the resistance of concrete to acidic water, sulfate attack, seawater in the case of corrosion, and freeze and thawing, ASR. Basically, all type of physical and chemical attacks will be beneficial from mineral admixtures. Okay. Again, this is due to pozzolanic reaction, which is have an effect on reduction in permeability as well as reduction in calcium hydroxide. It transfers calcium hydroxide into stronger and more durable CSH. Okay. So summary of SEMs on hardening properties, including the strength, gain. So for flash and slag, typically they will slow down the strength gain, especially at early age, but at later age it will catch up and exceed. For silica film, it will accelerate the strength gain at the beginning. Okay. For permeability, all these materials will reduce concrete permeability, so that is beneficial for concrete durability. For acidic reaction, it will also reduce reactivity, so increase the resistance, better chemical resistance. Okay, for carbonation, carbonation actually is a reaction between CO2 from the air with calcium hydroxide from the concrete. Carbonation will reduce the pH level in concrete. For carbonation, the effect is not as significant, okay, because this material will consume calcium hydroxide in concrete. Okay. The summary of advantage of SEM. Because pozzolanic reaction, they will remove calcium hydroxide. They will generate more CSH. So they will densify concrete, make it less permeable, improve the durability, reduce thermal cracking. So the temperature change will be less extreme, so reduce potential for thermal cracking. Improve workability and cohesiveness, so the fresh property of concrete will be better. Also reduce bleeding and segregation. The final strength will be higher, but the early strength may not be higher, depending on if we add flash, slag, or thicker film. For flash and slag, the early strength will be lower, but for silica film, the strength at all age will be higher. Alright, so today we have short introduction of flash, slag, silica film, slag, and some other pozzolans. Okay, but the major pozzolans are these four: flash, slag, silica film. Okay. So classification of flash, we have class C and class F, depending on the percentage of calcium oxide. And how do pozzolans affect the mechanical property of concrete? Go back to the previous slides. Okay. Durability will be higher, but the strength, depending on the age, may be higher or lower. Okay. And why pozzolans can improve the durability of concrete? This is because pozzolanic reaction. It transfers calcium hydroxide into CSH, make the concrete less permeable, less porosity, and also more higher stress. Okay. All right. Okay, so that's the end of this lecture number 4.